Welcome back. And now I guess we'll talk about midterm 2022. This was given in late March. The main thing about this is the first in-person or post-COVID exam that we have had in about 2 years. Halfway point in the course, what's expected from you, and generally what the topics are that are covered. So it's a standard sort of set of problems, and let's go take a look at them. So the main thing here is a 2,500 gram collar is released from rest at A, slides freely up the inclined, smooth aluminum rods, hitting a strike or hitting a stop at point B. So it's sliding over this right here, and it stops there with a velocity that's not given, but it's vis-a-vis. Distance between point A and point B along the rod is 3,000 centimeters, and the angle of inclination of the rod is 30 degrees so that's theta down here. At point A, the spring is inclined at 120 degrees from the horizontal axis. So the important thing here is to recognize this 120 degrees that is mentioned early on in the problem. If the unstretched length of the spring is 2,000 centimeters and the spring stiffness is K equals 1,000 newtons per centimeter. So it is a spring with a very large spring constant. You'll also notice that this has a lot of weird units: 2,500 grams, 2.5 kilos, 3,000 centimeters, 30 meters. All of this sort of plays into one of the stresses in the course, which is solving problems with units. And so keeping track of your units is really important here. So this is a problem with a lot of units. Calculate the spring extension at points A and B. Determine total work done by the collar as it moves from A to B. Determine the velocity vis-a-vis, which you were given or was mentioned at the beginning of the problem. And determine the rate at which work is done. So if I redraw this and I remember that 120 degrees, then I can see that that angle at the very top, which I'm going to call theta star, is equal to 30 degrees, which is equal to theta at the very bottom. So I'm given that. So mass of the collar is 2.5 kilos. Length is 30 meters. K is equal to 100,000 newtons per meter. So it's a very large number. Unstretched spring length is 20 meters. And theta is equal to 30 degrees. So a lot of large numbers in this problem. Spring extension is going to be this distance divided by sine of theta star. And theta star, again, is right here. And minus that 20 meters that you were given as the unstretched length over here. XAC then is equal to 25.9808 meters. That's a lot to include. And LOA can then be calculated directly as 51.9615 meters. From that, you know what the spring extension is. So spring extension, subtract 20 from that, and you get 31.96 meters. Spring extension at B, it's just going to be the distance LOA at that point, cos theta star, and YBC is just going to be LAB sine theta. And so you can calculate all of this. And once you do that, you end up with an SB of 10 meters. Okay, so you got all of the numbers, you got all of the relationships there, everything's good. We can calculate the work done. Work done is the difference in potential energy. So moves from point A to point B. Work from A to B is just going to be the negative delta Vs plus delta Vg. You're using T1 plus V1 plus work in A to B equals T2 plus V2. You can change that to delta. And you can calculate the change in potential energies for the spring at the beginning and the end. You get a really large number, 46 million joules negative. Change in gravitational energy is relatively small, at 367.9 joules. Total work done, add them up, and you can see right away that it's going to be well, it's a very small number, 4.61 times 10 to the 7th, and gravity doesn't play a role. So from that, you can calculate again the final velocity. Initial velocity is v sub a, work done from A to B equals the final kinetic energy. System starts with collar at rest, and initial kinetic energy is equal to 0. Work done from A to B is just 1/2, is then equal to 1/2 mcvb squared. We already have calculated all of the terms, and we can substitute it in, and we end up with 6,071.35 meters per second, or 6,071 meters per second. Rate at which work done is done by the spring force as the collar reaches point B. Express your answer in joules per second. You can be a bit clever about this and sort of say, well, it's change in work delta U over delta T. Instantaneously, delta U over delta T is the integral, or F dotted with dt or dx, and so you have delta x over delta T, which is V. So force, the force done at B times V. And substituting in terms, the force is the elastic force, which is 1 million. Substitute in terms, and you get 3.03 times 10 to the 9 watts. Really large numbers here, a little bit unrealistic, and however, it's more an exercise in unit consistency, angle distance relationships, work and energy, potential energy, and covers really sections 3.1 to 3.7, but a good chunk of the book. Second problem, small box of mass 3.5 kilos is located on the inside of a circular pipe of radius 2.3 meters as shown in the diagram. The origin is located at the center of the pipe. Coefficients of frictions are given as mu sub k 0.25, mu sub s of 0.65. Box. Assume the box is stationary. Draw a free body diagram of the box. What is the frictional force exerted by the pipe on the box? Express your answers in the xy coordinates shown. First part is just the box sitting there. Suppose the box is sliding down towards the bottom of the pipe with a speed of 4 meters per second at the instant shown in the diagrams. Determine the acceleration of the block in the coordinate system at the instant shown in this diagram. So remember, nt is specific to the particle, so it follows with the particle. And the other one is going to be xy, which is going to be at the center. So in terms of drawing this out, you have an xy coordinate, you have a weight acting downward, you have the force P which is acting onto this, and you then have a normal, that frictional force which is minus mu sub s, minus mu sub s n, or minus mu sub s p. The directions are given there, and the coordinate system was given as one that's vertical and horizontal, so that kind of limits you in terms of what you can do, but here's the forces. So weight in this case will be the total component, and friction and other terms will appear. So for the force tangential, mass times acceleration tangential is equal to 0, it's not moving. You have all of the terms, mg sine 20 minus force friction equals 0. Force friction is equal to 11.74 newtons. In xy coordinates, you then have to rotate it back, and you end up with two components, and you end up with this, minus 11 I plus 4.02 J newtons. The important thing to realize here is that it is actually easier to solve this problem in normal tangential components, because the only term that really needs geometry at this point is the mass, or the weight component. Everything else sort of is acting in the nt direction. So in this case, for example, force of friction would be aligned with tangential. Same diagram, but now you'll notice that I have flipped my coordinates. So before I had the xy like this, standard thing. But because I'm doing an nt coordinate, I can do this, and I hadn't have t in the direction of motion. So acceleration normal is equal to v squared divided by rho. Rho is 2.3 meters. V is given in the problem as 4 meters per second, and you get 6.96 meters per second squared. If you substitute in terms, you have unit consistency, and you have to worry about that. So sum of forces in the normal direction, mass times acceleration normal is 24.36 newtons, and you have P, which is acting upwards. You have weight, the component, acting downwards. Same thing with tangential. You have the weight and the friction force, and you combine everything together, and you end up with force P is 56.6 newtons, and the acceleration, after doing all the calculations, of 6.96 in the normal direction minus 0.69 in the tangential direction, meters per second squared. So here we have the kinematics problem. So typically we will ask you a kinematics problem because it's the halfway point of the course. Plane motion of a triangular plate is controlled by a crank, OA and DB. DB is 240 millimeters, OA is 60 millimeters. For the instant represented, OA and DB are vertical. This is really important. Keep an eye on that. OA has a clockwise angular velocity of 3 rads per second and a counterclockwise angular acceleration of 10 rads per second. Now, we have here the helpful axes, which, again, if you attend my lectures, you'll know that I tend to sort of go a bit overboard on this. Those axes are really important, even though you might know it absolutely perfectly. Draw the axes. Always draw the axes. If you get them on a problem, even better. Find the velocity of b at this instant, the angular velocity of db at this instant, the angular acceleration, and the acceleration of b. The angular acceleration is positive if counterclockwise, negative if clockwise. Okay, and it's, again, this is sort of what we've defined here. So, looking at the problem at this point, we have v sub b, which is equal to v sub a plus omega abc cross with rb with respect to a. And I'm just going to put the figure. db is constrained to move in I. I know that. That's here. And VA is constrained to move in I. I know this because the thing is vertical at this instant. It's fixed point rotation about point O and point D. And in both of these cases, it's rotating clockwise. And so I can put in the terms, I can solve through, and if you do that, you end up with a solution that tells you that, one, it's omega ABC is equal to 0, ABC being this rigid plate here, and VB equals VA. And the only reason you can do that is because you have two parallel vectors on the plate. If you have two parallel vectors, you can define it, or you can sort of inspect it and sort of say, let's just draw two radii of action here. Probably down would be better. But either way, they will never intersect. And if you do that, you'll find out that the instantaneous center is going to be infinite, in which case, again, the answer is omega ABC is equal to 0, and this plate is translating. So velocity B equals velocity of A, and you can calculate that to be 0.18 meters per second. Omega dB, the second one that you're not given, is going to be 0.75 rads per second. So in terms of the acceleration normal, I know those are going to be acting in towards the center of curvature. In both of those cases, point A is going to be pointing towards O, point B is going to be pointing towards D, and the acceleration tangential, because I'm kind of assuming in this right now, is going to be acting in the tangential direction. I've drawn it this way. Putting in all the terms, I say acceleration B is equal to acceleration A plus acceleration B with respect to A, and you can break it up into its normal and tangential components as done here, but then you have B with respect to A normal and tangential. Acceleration of B normal, you can calculate to be minus 0.24 alpha dB. Acceleration A normal, minus 0.54 J. you're given, in this case, or you know what the normal acceleration is. And let's see, sorry, you know the normal acceleration of B. You don't know its tangential acceleration. And for acceleration A tangential, you're given that information and you have that. So the only unknown here is alpha dB. Substituting in terms, omega AB is equal to 0. We know that. You end up with the normal acceleration of B with respect to A equal to 0. You don't know the angular acceleration of AB or ABC because you don't know necessarily that it will be. Substituting in terms and breaking it up into parts, you then have a solution in terms of alpha AB and alpha dB. You calculate that you actually have an acceleration alpha dB of 1.234 rads per second squared, counterclockwise. I didn't put a sign there because, and I didn't put a sign on alpha AB, which is above, right there, because I know that that term is clockwise. Acceleration of B, substituting back, putting in all the terms that I know, ends up being minus 0.3I minus 0.135J meters per second. All right, so this really wraps up the first half of the course. And the first half of the course is entirely based on particles. And we start to introduce rigid body kinematics, so the geometry of motion, not the forces causing the motion. And again, you have available to you at this point 3 years of past exams. And I understand 2022 is not a perfect, 2021 is not a perfect match to what's happened in the past because we have changed things over the year, or for that particular year, because it was entirely online. 2020 is closer to what has happened in the past, and 2022 is probably how I hope we move forward. So I continue to be hopeful, and we'll see how that works out. Thank you very much, and we will talk again.